We know in an IP network, that we have hosts and routers connect subnets. So in an example IP network, in an internet, we have subnets connected together via routers, the circles in my simple diagram, and we may have hosts attached to those subnets. So I just draw the subnet as a cloud here, where the subnet in practice could be, say, an Ethernet switch network. So one of those clouds may be where we have 3 hosts, those squares, and a router attached, the leftmost cloud there. In real life, it could be a switched LAN, where this is the switch, for example. Or it could be some other topology, some other network. The idea when we look at layer 3, the network layer, we allow any technology in here. And we want to be able to connect any host to any other host on any of those subnets. We have hosts, we have routers that connect the subnets together. We have IP routing that will find the best path through the network from sources to destination and create the routing tables. And then IP will tell us how to forward an IP datagram through the network. We looked at the structure of the IP datagram. Simply, we have some header and some data. And the header has a number of fields which we saw in one of our diagrams yesterday, including the source and destination address, and some other fields. We'll mention them as we need. We want to look at how the routing tables are used and how IP forwards data through the network. I'm going to use this example. And it's similar to what we have here, except in here it's a little bit more general, where we can say N routers. Okay? That is, our path from a source host to a destination host may consist of multiple routers. In this example, we're going to have 3 routers when we see the hosts. We'll look at the stack and the involvement of that before we go through how can we optimize, or how can we simplify the routing tables, and in general simplify routing in the internet so it becomes scalable. By scalable we mean when we increase from an internet which has 4 subnets and 12 hosts and 3 routers up to an internet that has hundreds of thousands of subnets, billions of hosts and tens of thousands of routers, then how can we make the routing tables small enough such that we can update them and maintain them? We know with a routing table we store the destination and what is the path to reach that destination. But one way we've got to simplify that information is, in fact, we don't store the entire path, we store the next hop in the path. So we in fact store the destination and the next hop in the path to reach that destination. That's one way to simplify the routing tables. We know that already. We'll go through 2 other ways to simplify. I'm going to give these devices some addresses. The hosts, the squares, just give them numbers. And the routers, the circles here, I'll give them, I'll just call it R1, R2, and R3. And in fact, we'll give the subnets addresses as well. So we can refer to, this is some subnet, subnet A, this is subnet B, C, and D. When we look at IP addresses, we'll see the exact structure of these addresses. Here we're using very simplified addresses. So let's create the routing tables for some of these devices. Let's start with host 1. All hosts and routers have a routing table. Let's start and draw the routing table with host 1. And we have 2 columns, we know. We have the destination and the next node in the path. You may not want to draw this routing table yet because you'll see I'm going to delete some parts of it and then update it. So maybe it's useful just to watch and then draw the final version. You'll see why in a moment. So host 1, this is a routing table for host 1. Let's say the destinations we're going to list are the other hosts in the internet. And we have 11 other hosts. Okay, to reach host 2, what do? What's our next node in the path to reach host 2? Here we're host 1. We want to reach our, if this is the source, this is the destination. What's the path to reach that? Remember, our internet is a packet switch network, a datagram packet switching network, where the packet switches are the routers. So remember back when we talked about routing and packet switch networks, we send from some source to a packet switch, to the next packet switch, eventually to the destination. So the path consisted of the source host, the set of packet switches, and the destination host. Now our packet switches are routers. So a path from source to destination goes via a set of routers. Unless we don't need to send to a router, in this case, the destination is on the same subnet as a source. We don't need to send to a router to reach this destination. If you refer back to our more detailed view of this cloud, looks like this. 1, 2, and 3, router R1. To send from 1 to 2, we say we can send direct via this subnet from 1 to 2. We don't need to send to a router because we don't need to send to another subnet. The role of a router is to connect 2 subnets together. But in this case, there's no need to send out to another subnet. So we can say that if host 1 is the source and host 2 is the destination, then we can send direct to host 2. I could say the next node is host 2. To reach host 2, the next node is host 2. We will make some simplification of the routing table and say if the destination is on the same subnet as the current node, then we say we can send direct to that node using the subnet technology. And in the routing tables, I'll just write direct here. That is, from host 1's perspective, it doesn't need a router to send to host 2. It can send direct to host 2 using the technology within the subnet, whatever it is. So just to make the routing tables, at least to explain that, I'll write direct here. In a real routing table, there will be some special notation included here. This means, from host 1's perspective, if it wants to send to 2, it looks in the routing table, it says direct. It means use the LAN technology to send. Use the MAC address, the MAC protocol to send from 1 direct to 2. We don't need a router in this case. To reach 3, we've got the same situation. On the same subnet, we'd send direct. To reach 4, what's the next node in the path? R1. Now we need to send to a router. 4 is on a different subnet. So from 1's perspective, we don't know the technology of this subnet. What we do is we send to a router, a packet switch, and then that router will deliver to the destination 4. So the next node here is R1. And we can keep going. 5 is R1, 6 is R1. To reach any of these three, we send to R1. 7, R1. From host 1's perspective, to reach host 7, the next node in the path, or the full path, is 1, R1, R2, 7. There's no other paths. In this simple internet, there's only one path to reach that destination. If we had some more subnets, there may be multiple paths. But in this simple example, just one path. So the next node in the path is R1. Keep drawing. 8 will be R1. 9 also R1. 10 also R1. To reach these three hosts, host 1 will send to router R1, and then R1 will need to forward on to the eventual destination. There's our routing table for host 1, if we consider just the hosts to be destinations. In this case, we have 12 hosts. In the internet, how many hosts do we have? Billions. So, and we don't know the exact number. If we were to use this approach for creating our routing table for my one computer, in the internet, I would need billions of rows in my routing table, which is just not possible to maintain such a table. And because hosts come and go in the internet, they turn on and turn off, they join and leave the network, this would need to be updated all the time. Storing this information is not manageable in a large network. So we can simplify it. We notice that to reach any host on subnet B, that is 4, 5 or 6, we send to R1. So instead of specifying a row for each host, 4, 5 and 6, we can have a single row that says to reach any host on this subnet, send to R1. So we could replace these three, 4, 5 and 6, with one special case, which is, and I'll use a different colour to make it clear, to reach any host on subnet B, so let's use the address B here, send to R1, where B is a special type of address. It's the address of a subnet, and we will use that when we look in the routing table to see, okay, if my destination is host 5, if we know that host 5 is on subnet B, then we know that we will send the datagram to router R1. So this represents host 4, 5 and 6 in our example. We can do the same for 7, 8 and 9. 7, 8 and 9 are replaced with subnet C. And 12, 11 and 10, 11 and 12. We've just reduced our routing table from, we had 11 entries down to 5 entries. More importantly, only one entry per subnet. So now, in the internet, if we have billions of hosts, but maybe tens of thousands of subnets, using this approach, we've reduced our routing table from billions of rows to tens of thousands of rows. We don't need an entry per host, we just need an entry per subnet in the internet. So that's a way to simplify the routing, and we take advantage of network-specific routing. We route to networks or to subnets, not to individual hosts. That is, using this approach, to reach host 11, we send to the subnet that host 11 is attached to. We'll send to R1, R1 will send to R2, aiming to get to subnet D. Once the datagram gets to subnet D, then it will be delivered directly to host 11. So that simplifies routing and in fact makes it manageable in a large network. one other way we can simplify this is from host 1's perspective. To reach B, we send to R1. To reach C, we send to R1. To reach D, we send to R1. If there were other subnets, E, F, G, we'd always send to R1, because from host 1's perspective, there's only one router it can send to reach other networks, R1. If there are thousands of other subnets out here, in all cases, host 1 would send to R1 to reach any of them. So we can say we can have a default route for host 1. And one way we could show that is to say star, which means any value. You know, star can be used as a wildcard to mean any value. So we can think of, we'll use this routing table to do some lookup and match the patterns. If host 1 has a datagram and the destination address is host 11, we want to send to destination host 11, then we look in the routing table. Does it match host 2? In fact, before we do that, we can simplify this as well. With our previous approach, hosts 2 and 3 can be replaced with subnet A. That is, any host on subnet A we send direct. That was using the previous simplification. Anyone else send to R1. So if we have an IP datagram destined to host 11, we look up the routing table. Is host 11 on subnet A? We need to know which subnet a host is attached to for this to work. So we have a destination 11. We look in the routing table and we ask, is host 11 on subnet A? We know when we look at this, no it's not, it's on subnet D. We will see later that the structure of IP addresses tells us the answer, whether a host is on a particular subnet. In this simple case, we can tell host 11 is not on subnet A, so this does not match. This will match. This matches any other value for the destination. 11 is some other value. Therefore, host 1 will know to send to R1. Send the datagram to R1. R1 will then use its routing table to deliver to the next hop, which is R2, R3, and eventually to host 11. So we've reduced our routing table for this host to just 2 entries. Covers the entire internet. For billions of hosts, hundreds of thousands of subnets, we just need 2 rows in our routing table. So that's the simplification for managing routing in the internet. We know that we store the next hop, not the entire path. We can refer to networks, not individual hosts, and we can have default routes, which covers any other value. What's the routing table for host 2? Your quiz next week? What's the routing table for host 2? Like this one. It's the same as this. Because host 2, again, to reach anyone on subnet A, send direct. And anyone else, host 2 will send to R1. So in fact, all the hosts on this subnet would have a routing table looking like this. Let's do 2 or 3 more routing tables. Quiz all the time. Any day. Any day. Maybe today. It's okay. 2 more weeks left. We can have a quiz anytime. Host 5. What do we create the routing table? B direct. A to reach anyone on B, which is our subnet from host 5's perspective, send direct, don't send to a router. To reach anyone on subnet A, send to R1. To reach anyone else, that is to reach C or D, we'd send to R2. So we could use star R2 here. Good. Routing table for R1. What's the routing table for R1? R1 attached to subnet A, so we'd send direct. A router is normally attached to 2 or more subnets, so it's also attached to subnet B. We can send direct. That is, we don't need to send to another router to reach anyone on subnet A or B. What else? Star, from R1's perspective, it can reach subnet A and B directly. C and D, it would send to R2. Anyone else, send to R2. And we could do similar for R2. I won't draw it. For R2, B and C would be direct. Subnet A to R1, subnet D to R3, or we could use star to R3. And similar for router R3, C and D direct, otherwise send to R2. Let's do that one. We may need it later. Destination next. From R3, C, we have a direct link. D, a direct link. Anyone else? R2. So all the devices would have routing tables. So you need to be able to create those routing tables or understand how they are created. Of course, this is a very simple example in that there are not many choices of paths. In real life, there may be multiple different paths to take through the network, but the routing tables would be adapted to support those different paths. How do we know what is the best path if we have multiple different paths? Our routing protocol does that. So we can think that there's a routing protocol always running, putting this data into the routing tables. In the Internet protocol, it does not specify which routing protocol to use. There are many to choose from, but what it relies on is that this data is in the routing tables. The Internet protocol will simply read these routing tables to determine who to send to. And that's what we'll demonstrate now. Any questions on how to create those routing tables? We want them as simple as possible, and that's by using the subnet addresses and the default routes, simplify those routing tables. Now let's use those routing tables to forward our datagram from source to destination. So our source, host 1, wants to send to host 11. Here's our datagram, the header. The source is host 1, destination host 11. There would be other fields in here. Go back several slides and let's remind us of some of those fields. This is our IP datagram, the header. That's this component here. There are multiple fields. Let's list some of them. The version, we're using IP version 4. The header length would indicate of how many options we have, if we have any options. One thing that we may need, or we'll explain, is the protocol field. What's the value? Or how do we determine the value? The protocol field. The version field indicates the version of the protocol. The protocol field indicates what?
IP version 4.
The version field indicates the version of IP. Protocol field indicates something else. It indicates the protocol that created the data. Yeah, the protocol that created the data in here. Yeah, the transport layer protocol, maybe TCP. That is, if we look at our stack now, and of course we have a source and destination which we've designated here. Host 1 in our case, the source host, creates some data to send to the destination. We assume in this case that we know the address of the destination. We need some mechanism to know that, but let's say I want to send data and I know its address of the destination server. My application creates some data, whatever the application I'm using, and there may be some application protocol that processes that, maybe adds a header. If it's web browsing, then HTTP is the application protocol. Sends that message to the transport protocol. We haven't covered them yet. TCP is an example transport protocol. There are others. That does some processing, creates a packet, and sends that packet to IP, the Internet Protocol. We're focusing on IP now. IP creates a datagram, adds an IP header, and the data in that datagram is what the transport protocol sent us. The protocol field is a number that indicates which transport protocol sent that to us. Each transport protocol has a number defined. You don't need to remember those numbers. TCP is one transport protocol. Number 6, UDP, I don't know if I can remember, is 17. ICMP is 1, and there are others. That'd be given to you if needed. Whatever transport protocol sent IP the data, then the protocol field takes the value. In our example, let's say it was TCP. So the protocol field would be 6. This is used because when the data arrives at the destination host, when this datagram arrives, then the destination host needs to know which transport protocol to send the data to. Do we deliver to TCP, UDP, or something else? We use the protocol field for that. So here's our IP datagram created by the IP software at our source host. Where is IP implemented in your computer? The operating system. So the operating system has some has some code which implements IP. So it's part of the OS. So it takes some data, creates a datagram, and then tries to send that. And the rules that IP follows at either a host and also at a router are simplified in this diagram. This shows the rules, the basic rules that it follows. How we read this diagram is that, okay, above this dashed line is the transport layer, below this dashed line is the data link layer. So everything between is IP. And it's some flow diagram that says what steps we take within IP. The first case we're considering is that the transport layer delivers data to IP. So we have some data that was created by our application, sent to the transport layer, and now is sent to IP. Included with that data, the transport layer tells IP what is the source address, that is, what is the address of the host that created it, what is the destination address, who do we want to send it to, and what protocol, that is the value 6. These 3 values, and possibly some other information, are given to the IP software as well as the data. IP creates an IP datagram which looks like this, well, conceptually. That is, IP takes the data that it receives, creates a header, fills in the fields of the header with the appropriate values, and then we can see the next step is that we compare the destination IP address, 11, with our IP address. So the device which is processing this IP datagram, it knows its own IP address, currently on this device with IP address 1. It compares, does the destination match my IP address? No, it does not. Destination is 11, I'm host 1. No, then we use our routing table to determine who to send it to. That is, if I have an IP datagram and I'm not the destination of that, then I'll use my routing table to send it to someone else. So no, is the destination in the routing table? Destination is 11. We look up the routing table. Is it in the routing table? Yes, it is, because in fact it matches this row. Destination 11 is not on subnet A, it doesn't match this row, but this matches any destination or any other destination. So we say that we have a destination 11, we look in the routing table tells us to reach destination 11, send to R1. So we find who is the next node, the next hop to reach the destination. In our example, it's R1. And then we send this datagram to R1 by sending it to the lower layer, the data link layer. So we send it to the data link layer, the datagram, IP header, and also the next hop, which is R1 in our case. We go back. We're at this point. In host 1, we received some data, IP did the processing, determined it needed to send that datagram to R1. Sends to the data link layer. Maybe it's an Ethernet data link layer. Maybe you're using Ethernet LAN. It will follow its rules, create some signal to transmit across the link, and it will be received by R1. And eventually received by R1 and passed up to the IP software on R1, router 1. That is, this datagram that was sent by host 1 will be transmitted across our subnet from here to here, and R1 will receive that datagram. And then within the IP software within R1, it will process that datagram using the same rules that we have on the flow diagram. Easy so far? Any questions? What? You want a quiz? What's the question? Any questions? So if we have a quiz at the end of this lecture, you'll be okay? Why not? What's the problem? What we've done so far is we started with host 1 and we're focusing on how do we forward this datagram through the internet to the destination. We're focusing on what IP does at each of these devices, at the host and at the routers. And the steps that IP takes are summarized in this diagram. In that, at host 1, we received data from the transport layer, created a datagram, this. The datagram was not destined to us, so we looked in our routing table, we found the row that matched and found the destination of this datagram to be R1. So we found the next hop in our path to be R1, and we send that via our data link layer to R1. So we've sent our datagram, our IP datagram, from host 1 to R1. How do we send it over the data link layer? Depends upon what data link layer is being used, what subnet technology is being used. From IP's perspective, we don't care. Whatever can get it across that link. Note that so this is the IP datagram. Just the source address is 1, destination is 11. That's what we have here. R1 receives this datagram. It receives the datagram from the data link layer. So we use this diagram to see what router R1 does. This is when we receive data from the transport layer. This block is when we receive it from the data link layer. That is, we've received it on our link. We've got the datagram. We check, does the destination address of the datagram, 11, match my address? R1, all of the routers have IP addresses, or have addresses. R1's address in our simple example is R1. Of course, it does not match. That is, this datagram is not destined to R1, it's destined to someone else. So no, therefore R1 looks in its routing table. R1 has a datagram destined to 11. R1's routing table is here. 11 is not on subnet A. It is not on subnet B. Therefore, this row matches. We send to R2. So we find the next hop to send to, which is R2, and send it from R1 to R2. The same datagram. There are only some small things that may have changed in the header. The source and destination are still the same. Source is the original source, destination the final destination. So that was this step, that is the processing of the datagram within IP at router 1, decided to send it to router 2 based on the routing table, transmits it across the link, and it's received by router 2. And router 2 will do the same. Receives the datagram. Is the destination me? No, it's destined to 11. Check my routing table. We don't have the routing table for router 2, but we'll see you can create it and it should send to router 3. From the routing table, the next hop to reach the destination is router 3. Transmit to router 3. And I'm going to go down here. The datagram is transmitted to 3. Same source, same destination. 3 receives, does the same. Receive, it's not destined to me. Look in my routing table. What happens? Which row matches in the routing table?
Routing table go to subnet D.
D. So the second row. The destination is 11. We magically know that host 11 is on subnet D.
Magically no.
Yes, we have magic. The magic we'll see when we look at IP addresses at the end of this lecture. There's some way that we know that destination host 11 is on subnet D. We'll explain that later, but we assume that we know it's on subnet D. So it's not on subnet C, it is on subnet D. This is the router 3 that's doing the check. Therefore, router 3 knows to send direct to the host because the destination is on the same subnet as the current router. So we look up the routing table. Direct here we interpret as use the subnet technology to deliver this datagram to that host. We send to the data link layer, transmit across the data link layer, and it's going to be received by our host. datagram with a source of 1 and destination of 11. The host receives the datagram. Step here, we receive a datagram. Is the destination of this datagram the same as my IP address? Yes. I am host 11. I've received a datagram destined to 11. So yes, I am the destination. So now, remove the IP header, take just the data, and send that data to the higher layer, to the transport protocol. Which transport protocol is determined by the protocol number in the header. The transport protocol will process, send to the application layer, the application will process, and then you have the data. So that's when the destination host receives it, IP removes the header and sends the contained data to the transport layer, which then sends it to the application, and then we've received the data at the destination application. So that's how IP uses the routing protocols and the datagram, and in particular the header fields, to forward an IP datagram through the internet. It's reasonably simple. As a protocol, there's no concept of acknowledgements. We've seen in the flow control protocols, we send data, get an ACK back, sequence numbers are important, window sizes. There's no concept like that. We just create a datagram, use our routing table to determine who to send it to, the next hop, and the routers do the same thing. When they receive a datagram, they determine who to send it to until it reaches the destination. And once the destination receives that datagram, they process the data. They remove the header and consume that data. So that's the basics of IP forwarding. And that's how we communicate across the internet. The routers are distributed across the internet. So, for example, my laptop, for SIT, there may be, in fact, there are multiple routers, but let's say that there is just one router in SIT which is at the edge of this campus. That is the link from this campus to the wide area network. There's a router there. So my laptop sends to that router sends across the next link, and each of these routers have routing tables to determine if I want to send to google.com, I need to know the IP address. The routing tables that have entries in them, they look them up, and those entries will tell them what path to take to reach the Google web server based on the IP address. Any questions now on how IP forwarding works?
Suppose I request for Forwawrding.com, right? And then, when the internal network and the wide network has different kind of addresses. So, normally, when you request for the website, right, and the website and the web server has to respond back to me. The thing is, we have different kind of network class, and then.
So the question is about, okay, normally when we send, there's different issues. There's the issue of, usually within organisations, we have a certain type of IP address. You may see your IP address at maybe 10.0.0.3 or something, or 192.168.0.5 at home perhaps. Whereas the Google web server that we want to send to has a 72.13.10.5. We're going to see the structure of IP addresses shortly, and then we'll answer your question. The question is about how do we translate between these different types of IP addresses. We need to explain the structure of IP addresses to answer that, but that will come up. So, again, exam or quiz question, what could it be? Create the routing tables. Well, that's easy. We know how to create routing tables from the routing topic. we create it based on the least cost paths. In quiz 5, you created a routing table based upon, you were given some least cost paths. We haven't gone through the steps of how to calculate the least cost paths. In this simple case, it's simple. There's just one path from 1 to 11 because of the structure of the network. But if you know the paths, then you can create the routing table. Using these 3 simplifications, include the next node, not the entire path. Some of you gave answers in quiz 5 which included the entire path in the routing table. I subtracted a mark for that. Yes, yes, it can include cost. But
if the question have cost, we have to include.
No, you don't have to include unless it asks for it. In the quiz, if you included cost, you were wrong because you didn't know what the cost was.
We assume.
You assumed something was not right.
We assume.
There was no cost in the quiz. But yes, this is a simple view of the routing table. And the notation I use here of direct and star is just to explain. In a real routing table, it doesn't say direct, it doesn't say star. There are special values that can be used here. But this is the concept. The simplifications include the next node in the path, not the entire path. Route to networks where possible, not to individual hosts. Use an entry to route to a particular subnet, not to all the hosts on that subnet. And use default routes where possible. Any questions before we move on to the last part of IP? No quiz today. What have we got? Two more parts about IP. Fragmentation and reassembly. And before we go through that one, we can quickly cover the Datagram Lifetime. Remember, if you go back to the structure of the IP header, there's another field which is called time to live, TTL. So that's another field in the IP header. The time to live. This is like a hop limit in our flooding protocol. In flooding, remember, in flooding, if we use a hop limit of 4, the idea is that that packet will only go across 4 hops and then will no longer be sent. It's limited to cover 4 hops. Same as the TTL field in the IP datagram. It limits the lifetime of that datagram. So if we set the TTL to 4, then our host can send it to the router. That's 1 hop. Then the router to router, it can traverse 3 hops. And then if it hasn't reached the... it can traverse 4 hops. If it hasn't reached the destination, the router will discard. It would delete that datagram. It would no longer transmit. In our case, if we had a TTL of 2, we wouldn't have reached the destination. 1, 2 hops. This router would receive it. The TTL would be decreased to 0. It would not send on. So the TTL is decreased every hop we transmit it until it reaches 0, at which point it's not sent any further.
We have no data about how
it's supposed to be a measure of time to live. The way that we, rather than having specific, using clocks within the devices and keeping track of time, we just count in terms of number of hops. That is, in theory, we could say, okay, this datagram can live for 3.5 seconds. But that would mean we'd need to count, we'd have clocks at each device and know the time when it was sent and the time when it was received, and the clocks at the devices would need to be synchronized. That's very hard in a large network. So in practice, what we do is we say, this datagram can be sent 4 hops to approximate some time that it's allowed to live. So time to live is really measured in hops to live. Measuring real time is too hard in a distributed network. It's useful if we have errors in the network. That is, the routing tables are configured such that R1 sends to R2 and R2 sends back to R1. If there was some error in the configuration of the routing tables, maybe you go out and get a job at an internet service provider and your job is to configure the routing table, but you make a mistake and you say the routing table for R1 send to R2 and the routing table for R2 send back to R1. We'd have some loop. We'd send our data to R1, to R2. R2 would not send to R3 but back to R1, and they keep sending to each other. If we have such an error, this time to live helps us because eventually the packet will stop to be transmitted. It would not be sent forever in the internet. So that's the TTL. Going back, fragmentation and reassembly. Our subnets normally specify the maximum size of a frame that we can send across the subnet. In Ethernet, the maximum size frame was 1,500 bytes. So if we have a datagram larger than 1,500 bytes, 3,000 bytes, we need to fragment it because we cannot send anything larger than the size specified by the subnet technology. Different subnet technologies may have a different maximum sizes. Ethernet may specify 1,500, something else may specify 500, and something else 200. So we need to sometimes fragment our datagrams into smaller pieces and then eventually reassemble them back into the original datagram. That's what fragmentation and reassembly does. There are three basic approaches. Let's go through them through these examples. In this example, we have three subnets. Consider the top example first. We have 6,000 bytes to send from source to destination. Here's the path we're going to take. And the subnets have maximum packet sizes that they're allowed to transmit. First one, 2,000 bytes. Second one, 1,000 bytes. Third one, 8,000 bytes. Just different maximum sizes. In the first approach, so the difference between these three approaches, and in general for fragmentation and reassembly, where do you fragment and where do you reassemble?
The fragmentation and reassembly should be in the divisible number, in the factor.
No, doesn't have to be.
500, 200.
No. There's no relationship between these numbers. No. This can be 112. Different technologies will choose a value what they think is most appropriate. We'll see there are three ways to deal with it. The first way is the source, if it knows the minimum of the maximums across the path. Note that the maximum on this subnet is 2,000, here it's 1,000, here it's 8,000. If the source knows the minimum of these three values, the minimum is 1,000, then it fragments its original data into sizes no larger than that minimum. So we start with 6,000. We know that along our path to destination, this subnet limits us to 1,000. The others are larger. Therefore, at the source, fragment into 6 fragments, each containing 1,000 bytes. So in this case, we fragment at the source and only at the source. We create 6 fragments, all of 1,000 bytes. They are sent across the first subnet. The subnet allows us to send 2,000 byte fragments. We've got 1,000 byte fragments, that's okay. So it's within the limit. Send those 6 to the first router. This subnet allows 1,000 bytes. We have 6 fragments, all of 1,000 bytes. Send them across that subnet. The last subnet allows 8,000 bytes. We only have 1,000 byte fragments. Send them all. The destination will receive those 6 1,000 byte fragments and reassemble. Put them back together, and we get the original 6,000 bytes of data. So this is an example of fragment only at the source, reassemble only at the destination. For this to work, the source needs to know the maximum sizes supported by all the subnets in the path. That's not easy in some cases. What's your path from here to the Google web server in California? You need to know the set of subnets that you send via and their maximum sizes. Well, that takes some effort to learn that information. Another approach, the second diagram.
So the first one is not used.
The first one can be used. It's not used by IP.
Not used by IP, but used
Can be, in general, it could be used in a network, in an internet. We'll say, we'll look at the trade-offs of all 3 and then compare them.
But for IP, it's too large to know.
The problem with this, the main problem with this one is the source device, say my laptop, needs to know about the entire path to the destination. That is, my laptop needs to know that the packet is going to go on this path, not on some other path. And that becomes difficult. It's hard to know that information. Second approach, fragment at the source and or at the routers. Reassemble only at the destination. In this case, we don't need to know about the entire path. We just need to know the maximum size of the next subnet. Let's see how it works. We have 6,000 bytes. Source needs to send to router 1. It knows the maximum size supported by this subnet is 2,000. Therefore, we need to fragment into 3 fragments of 2,000 each. Okay, so send those 3 fragments to router 1. Router 1 receives the 3 fragments. The first one is 2,000 bytes, so the second and the third. The router 1 knows over this next subnet we have a maximum size of 1,000. So we need to fragment again. We have 2,000 bytes. The maximum size we can send is 1,000. So the first fragment is broken into 2 fragments, the second one into the next 2, and the third one into the next 2. As a result, we'll get 6 fragments, each of 1,000 bytes in length.
Or if the first come, say, 1,200, and the next should be 600, 1,200, and then we divide by 2.
We divide by, we break our break the packets that we receive into fragments which are no larger than the maximum size supported.
Up to.
Yeah, no larger than. We can be smaller. So it could be.
But have to divide equally.
We don't have to. We normally would. We'd normally want to achieve we want to send fragments of the maximum size allowed. Because the larger the size, the smaller the header and the more efficient we are. So the goal in all of these cases, the ideal case, is to send fragments which are the maximum size allowed. Therefore, we usually break it into the maximum.
For the next router, the maximum size is still smaller than the previous.
Then we'll need to fragment again. We cannot send anything. If the maximum size is smaller than the previous, then we'll need to fragment because we cannot send anything larger than the maximum size. So this second case, we're fragmenting along the way. That's the difference between the second one and the first one. The first one, we fragment only at the source. The second one, we can fragment at the source and at the routers. The source sends 2,000 byte fragments to router 1. Router 1 needs to break them up into 1,000 byte fragments, sends to router 2. Router 2 has 1,000 byte fragments. It can support 8,000. It sends them as is. It does not reassemble. So this second approach, the rule is fragment at source and possibly at routers, reassemble only at the destination. The first approach, fragment only at the source, reassemble only at the destination.
So in the second approach, if the datagram meet the router that very minimum allowance, so the rest of the traffic will be small at that.
Yes, it will never get bigger along the path.
So it will not
That's
grow.
right. The third approach, it gets bigger. That is, the third approach, fragment at the source and the routers, reassemble at the routers and the destination. Start with 6,000. This subnet supports 2,000, so we must fragment 3 2,000 byte fragments. Router receives those 3, puts them back together. The router reassembles, and we have 6,000 byte original data. We reassemble. And now consider this segment supports 1,000, so we have 6,000, we divide into 6 fragments of 1,000. Transmit them. Router 2 reassembles, we have 6,000. This subnet supports 8,000. We have a 6,000 byte packet, no need to fragment. Transmit as is, and we receive as is. And no need to reassemble here, only if necessary.
And this is, I think, have time to process more than that.
So let's compare these now in advantages, disadvantages. This one, the disadvantage is that the source needs to know the entire path. In these two, you just need to know the next subnet. That's much easier. In this one, it's simple because only the source and destination fragment and reassemble. The routers do not. That saves time at processing at the routers. In the second approach, well, let's go to the third approach. The third approach is good because we don't need to know the entire path. It's good because we send optimal size fragments across each subnet. We want to send fragments as large as possible. Here, large as possible is 2,000. We send 2,000. Here, 1,000. We send 1,000. Here, 8,000. We only have 6,000 bytes of data. So the largest we can send is 6,000. This is the most efficient because it reduces the number of headers. The larger the frame or the larger the segment, the less the header contributes to overhead. This is good because we don't need to know the entire path. This is good because we are efficient in sending large size fragments. This is bad because each router must reassemble and fragment. That introduces processing delay. This is a trade-off of the two. The second one is sort of in between. We send different size fragments across the subnets, but sometimes not the maximum. We saw 2,000, 1,000, but here we were less efficient than this case because we send 6 fragments, here we just send 1. So this one's less efficient than the third case, but it doesn't require reassembly at all the routers, so less processing than the third case. It doesn't require the source to know the entire path like the first case. So it's in fact in between of the first and the third. That's what IP uses. The Internet Protocol uses the second case.
Why we have those standard for package, so we don't know everything. Just standard that every package would be 1,000 bytes, and everyone follow this rule.
Remember, the internet working is about connecting different LANs and wide area networks together. Different organizations have different requirements. and therefore they make trade-offs as to what's the best maximum size for their technology within their LAN or within their wide area network. So you may choose within SIT the best size is 1,500, but someone else who has to build their network or choose a technology think it's better for their purpose to use 500 bytes. Across the world, we cannot all agree upon what's the best. There are different trade-offs. Therefore, we have to deal with these differences. That's IP covered. We know that we've gone through how to forward the datagram through an internet. We've briefly looked at fragmentation and reassembly and also time to live. In the last 5 minutes, we just want to introduce addresses to give you some practice before next week. This slide just gives an example of how the fragmentation works with respect to the headers. Now, in my example here, I said the address was number 1. The address of the router was R1. The address of the subnet was A. That's not true in IP. IP has a specific format of the addresses. We need to learn how that IP address is structured. An IP address is 32 bits in length, an IP version 4 address, and that's what we're dealing with. That is, this address in the source field is the 32-bit value, so is the destination. Of those 32 bits, some of the bits will be used to indicate the network or the subnet a device is attached to, and the remaining bits will be used to indicate that device on that subnet. As an example, I said this was host 1 attached to subnet A. We could say, in fact, that the address of this is A1. This portion indicates the subnet. This indicates the host on that subnet. This one would be A2. This would be A3. This would be B4. If we were to use this format where our address indicates two things, our subnet and the host on that subnet, or the device on that subnet. We'll see the structure of how that 32 bits are split to indicate what is the subnet and what is the device. Note that routers have addresses as well. This router is attached to two subnets. It would need two IP addresses.
Why this not B1?
Which it could be B1. What's important is that there's two things in this address. Something that identifies the subnet, B, and something that identifies the device, 4. The value, this could be B1, but they all need to be B something. The router is attached to subnet A, so it may have address A, let's call it A10. Just continue our example here. A1, A2, A3, A10. This router is also attached to subnet B. It would have an address here, say B10. So a router would have an address for each subnet it's attached to.
Different address in different subnet. The view of A is A10 and the view of B is B10 for router A, B1 and router R1.
Let's state the rules. All the devices in one subnet must have the same network portion. They must be all A. That's the first rule. All the devices in this subnet must be B something. That's the first rule. All the subnets in our internet must have unique network portions. A, B, C, D. We cannot have A, B, 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 because these three subnets would not be unique. And all the devices within one subnet must have unique host portions. 1, 2, 3, 10. It cannot be 1, 1, 1, 10. The host portion would be not unique. So that's what's required for our addresses. Except IP addresses are not letters and numbers, they're a 32-bit value. And some bits represent the subnet, some represent the host. To give you an example, no, we will not go any more of how that 32 bits is split up. We'll cover that next week. But because it's a 32-bit number, that's what the computers deal with, 32-bit values. What us humans want to deal with is something a little bit simpler to write down and remember. So there's a way to convert a binary IP address into what's called the dotted decimal notation. Let's just cover how that works so you can practice. Here's a 32-bit address. We want to convert it into a notation that is easier to write and read for us humans. The approach is that we divide this 32 bits into 4 8-bit values and then convert each 8-bit value into a decimal number. What's the first decimal number here? Anyone can work it out? We have 1, 1, followed by 6 zeros. Where this is the most significant bit. In decimal, 192. You can use your calculator. 128 plus 64, 192. The next 8 bits, what is it? I can't remember. Next. Is it 228? You can check. The next 8 bits, so that was from here, is I think 17. And the last 8 bits, 57, or close to 57. So the approach, you have 32 bits, divided into blocks of 4 bits, of 8 bits, convert each 8-bit number into a decimal number. And in this example, we get 192, 228, 1757, or something similar to that. You can check. And then combine those separated by dots. 192.228.17.57. That is the IP address represented in dotted decimal notation. Every IP address, we can do that conversion. And we can go back. If I give you this, you can find this. You can use a calculator. That's not the problem here. Just know the procedure of converting. Because when we go through all our examples, we will talk mostly in this form, dotted decimal notation. But understand it's a 32-bit value. And understand how to obtain that. So next week what we'll do is explain, of these 32 bits, which bits represent the subnet, like the letter A, and which bits represent the host, like the number 1. And look at different ways that we can split between the network and the host portion. And we'll use this approach when we explain. So let's finish there. Attempt some conversions. So just so you can quickly understand how to convert between binary and dotted decimal for an IP address. And then we'll explain the structure next week.